Hello and welcome. We continue on with our exploratory research journey to look at the problem of design generalized functional observer for a more general class of time delay systems, where now we have multiple delays in the stack vector as well as in the output measurement vector. And what we like to do here is to estimate this generalized functional with containing multiple delays in there. And if you can recall in our previous discussions, particularly in chapter 5, where we look at the estimation of an unknown input for a system with a time delay in the stack in the output measurement vector. And when we did the decomposition, we impose a constraint on the matrix C. And with that constraint on matrix C, we arrive at two conditions. This is the condition that gives rise to that class of time delay system. So what this one requires is the matrix, the row associated with matrix CD, that row in there is a null space of matrix D, which D is an unknown associated with the unknown input in here. And so we obtain this very complex time delay system with multiple delays, especially multiple delays in the output measurement vector. And that the reason why we undertook our exploratory journey to look at how we go about design functional observers, generalized functional observers, and so on. And that's what we did in chapter 12, sorry. We took exploratory journey. And so we started with chapter 12, where we say, look, let's investigate function of it, and then look at a bit more delay terms in there. Bear in mind that at the time there was no methods available, and that's the reason for the exploratory nature of our book. Now, what we like to do here is to discuss this general functional. So we're going to skip the development in chapter 12, and the reader can have a look at them. What we like to do is we want to do the generalized functional observers for estimating these general functionals. And when we look at it, these matrices, they are associated with the decomposition of the unknown input. So when you look at that, we call this bit here F, and then FD, and then FDD, and F3D. So basically associated with 3 delays in there. And all the associated matrices, they're all well defined. So we all know them. They are known matrices. Okay. So this is what we're going to do, and we basically discuss what happened in chapter 15. We're going to do it a fairly quick discussion because we all have the good idea how we go about doing it. Okay. So what we do in here is we say, okay, we're going to estimate that generalized functionals. And this is the structure for it. This is the observer structure. When we look at this observer structure, we see that, wow, now it contains multiple delays, as well as it also contains this uh, delay, which is the internal delay. So we not only have an observer with an internal delay, but with multiple internal delays. The reason for having this extra term in here is it would basically relax the conservativeness of our existing conditions. And if we have a look at the discussion in chapter 12, for example, uh, the discussion in chapter 12 where we show that by having this um, extra term in our observer structure, we could realize an observer, which is the first order observer with multiple delays. Okay. So there was an example in this chapter, and during the process of finding a generalized functional observer for this example, we found that an observer with a first order with an internal delay does not exist. In other words, it's we cannot ensure asymptotic stability when we design a generalized functional observer to estimate the given this given stack variable. In fact, it's just an observer, just a standard functional observer to estimate the second stack variable in there. So we couldn't find a first order observer with an internal delay, and it's unstable here. Whereas when we employ an observer with multiple internal delays, in other words, with two internal delays, we manage to stabilize the aerodynamic equation. And just to show that, so basically that example to show that in fact the structure of the observer that includes an internal delay, extra internal delay in here, can relax the existence of the observer condition. So that was what happened in chapter 12, where we look at just a standard uh, stack observer. In other words, we only estimate the second unmeasurable variable. We also show that the employment of this general structure observer can help to find a suitable observer, which is first order. And then we also show in there we could have example 2 in chapter 12. We also find that if we do it with a more generalized functional, then we can also increase the order of the desired observer. Okay. And thus it's illustrate very well the situation that we can overcome some existing difficulties in the conventional linear functional observer, and by extending that idea to include delayed functional, we can then have a higher order observer, which can ensure asymptotic stability. Okay, so that was what happened in chapter 12. And so the idea here is we have a much more general observer structure. And so we have, these are all the observer unknown matrices. We have how many? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 or something along the way there. And so how do we find them? How do we find them so that the estimation of this generalized functional converges asymptotically to the generalized functional itself as time goes to infinity? Okay, so that's what the aim is. And the estimation of this generalized functional, of course, is used to realize the asymptotic estimation of the unknown input, where this entire things here is replaced by a direct estimation in one go. That's the idea behind that. So if you look at it from the historical perspective, there was no methods available at the time. Nobody looked at the asymptotic unknown input estimation, and that's the result. That's why generalized functional observers were not introduced at the time. We only found out when we actually started to investigate the asymptotic unknown input estimation of time delay systems with a specific structure where the delay occur in the output measurement vector. Okay. So that's the background behind that, and this is the development. This is the new observer structure. And how did we come up with this? Of course, there was a bit of adjustment here and there, and it's a refined process of picking out an appropriate structure, which is general enough, and it's also enough for us to demonstrate the theory behind it. Okay, so just like what we adopted in our previous developments, we can apply our unified framework for deriving the existing conditions. And so what we do is we say, okay, let's adopt the same framework, taking the error vector, which is the difference between the two functionals. One is the estimated functional, and the other one is the true functional itself. And then taking the differentiation of the error equation by substituting whatever the structure we propose in here and the functional cell. Remember, this functional cell has three internal three delays in there. It has actually has 3,000 here, so it's pretty general enough. And along the way, when we do the differentiation of both sides, it's just very straightforward. To be honest, it's just a matter of careful. You have to be careful, otherwise we make mistakes in there. We just have careful evaluation, taking the differentiation and a systematic way of expanding and substitution and all that stuff in, we arrive at a very tidy expression in here. And when we observe in this aerodynamic equation, we have this time delay system here. And have a look at that. It's actually a time delay system with multiple delays. So we want to ensure the asymptotic stability of this aerodynamic equation. And to ensure that, we also have to force all of these terms in here equal to 0. In other words, have a look at this thing. That is not a problem because we can always choose the observer matrix J, JD, and so on. Have a look at the structure here. There are 4 unknown observer matrices associated to the output measurement vector. They can be explicitly obtained in terms of the matrix M, MD, and the rest of those matrices regarding the generalized functional. Okay, so that's not an issue for us. The thing that we need to really concentrate on is the terms associated with these expression. So when we look at these terms, we have x bar 1 of t, delay 1, delay 2, delay 3, 4, 5. So we have actually altogether 6 couple matrix equations. 6 couple matrix equation. All right. And that where when we presented the existing conditions, we have all of this stuff in there. We have this 1, 2, 3, 4, 5, 6, and we just use this notation to define them. For example, J here is really the thing in here, there, and it is specified explicitly in here. That thing there has to be 0. So we have 1, 2, 3, 4, 5, 6, 6 couple matrix equations, and altogether in there we have something like how many unknowns in there. So we have something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 unknown matrices, and we stuck those 6 couple matrix equation into an augmented form, just like what we used to do in our previous discussions. So you can see that the framework here is very unified, and it's nothing really um, um, uh, extraordinary. Basically, we use the unified framework. We define the error vector. We take the differentiation and we propose the structure, and then we fit that in, and then we arrive at the 6 matrix equations. So you see that it's actually a bigger matrix now. And then once we know how to solve for these unknown matrices, in other words, we can obtain the if and only if condition for the existence of a solution, which is basically this solution of a matrix X in here. And when we stack them all together, we have a look at this big matrix compared to the previous one. Remember, we had something like 4 columns, something like that. Now we have 6 column blocks in there. And when we examine this matrix, we have all those uh, F matrices associated with the generalized function. So this row block in here associated with the unknown metric n, yeah, unknown metric n, and then the next row block, the next row block is that, and the next row block is that. And so when we have this big matrix expressed in this form, the existence condition, the if and only if, is basically the rank of this left-hand side equal the rank of this right-hand side. And if it's satisfied, let's say if it is satisfied, what do we do next? Just like what we did before, we get a generalized solution, and then we can exploit the extra degree of freedom, and then from there we want to ensure that this aerodynamic equation is stable. And if the extra freedom in the solution of this generalized uh, equation is satisfied, then we can further do the stabilization of the time delay error system. And that's basically the entire approach for this particular observer designed for uh, functionals, which basically in this form here, okay? And along the way, when we once we got the solution, once we achieve the asymptotic stability of this aerodynamic equation, of course, the rest of the observer parameters can be obtained. And so when we look at this big matrix, we have is also y hat in here and all of that. And so that allows us to obtain this unknown observer gain matrix as well. And when we examine this matrix in here, that one, all those matrices, they all well defined. in the book. So like for example, that one is defined, that one defined, as well as some other terms like C1 bar or C bar 1 and so on. They're all well defined in the book. So with this big matrix and the check in the rank condition, we basically just test the condition, and if it's satisfied, then we can realize the solution, and then we can go to the next stage, which is ensuring the stability of it. And of course, we can always pick and choose different structure for the observer. For instance, from the practical point of view, if we go ahead design an observer for a given um, time delay system like the one we consider in here, we might like to start with the one without internal delays. So we might just let ND and DD equal to 0. In that case, the condition becomes more restrictive because we got a less number of rows in this matrix, and there's a high chance that the condition not satisfied. But again, that will ensure that we're going to have a much more practical, simpler observer, which is independent. The error is independent of the time delay. And so that's the discussion regarding how we go about doing the design of a generalized functional to realize the estimation of this generalized functional. Okay. Um, what we like to do is in the next video, because if I discuss the numerical examples, then it might be a bit too long to do it. So we like to defer the discussion of the numerical examples to the next video. For this video, we basically outline that a method, the idea of how to go about design a generalized functional observers to estimate generalized functionals for this class of time delay systems is basically following a straightforward approach that we adopted in this book. Um, the thing about this is the structure of the observer and a systematic derivation of the existing conditions. Okay, so that's basically the discussion, and we will just head up what we do in the next video. We're going to take a few numerical examples. Okay, the first one is we're going to do a comparative analysis. So we're going to further demonstrate the advantage of estimating the generalized functional directly instead of using this approach in here. Okay. In this approach in here, what we do is we estimate the stack vector x bar 1 of t, and then we delay it by tau. And then we delay it by 2 taus, and then we delay it by 3 taus to realize this generalized functional. Okay. And then we do the other option, which is we estimate directly. If you recall from our previous discussion, we already demonstrated the advantage of estimating a generalized functional observer directly, and that's in terms of lesser hardware components and better chance and response. And this will basically tell us that. Just further reinforce that. In doing this numerical example, we systematically explain the process behind that. Okay. And just a head up, we're going to have an observer, which is a very high order to be to our amazement, especially when we were looking for an observer without an internal delay, without internal delays. And using the idea of augmentation approach, inserting more rows in there, we arrive at an observer, which is a fifth order observer to estimate the stack variables in there. Okay, so that is something very intriguing. As you can see, the idea of the estimation of time delay system with multiple delays in the stack and output measurements, and the idea of estimating these generalized functionals, the order of observer can go beyond the dimension or the number of stack variables. Okay. And bear in mind that the approach that we are doing here is based on our systematic framework at a sub-level. People can come up with alternative design methods, for example, to addressing this problem. But since this is the first time we introduce it, so that's why we just adopted our generalized framework, which is what we explained in this presentation. We took the error vector and then we based on that and we took the differentiation of it and then we derived the existing conditions systematically. Okay, systematically. So thank you very much for watching, and I see you again in the next video, where in the next video we will look at numerical examples to illustrate the design of generalized functional observers to estimate this generalized function. Okay, thank you very much, and bye bye for now.